All right, hey, this is Horner. We're going to take a look at work and conservation of energy, and this is part 5. This chart's really very useful. It shows you some things that are happening in terms of the angle between the force and the direction of the motion. So direction of the motion you'll see is just by the displacement here, delta r, and our force is the red vector, which is F, and then our velocity, you will see it down here on the bottom, and kind of what's happening to the velocity. So here's our original velocity and our final velocity. If my angle between the force and that change in position is 0, then we know that the work is just F delta R, and the sign is positive. Here we've got energy transferred into the system, so our kinetic energy goes up and the particle does speed up. I can also do the same thing by pushing it, but pushing it at an angle. So when I push it at an angle and it's still moving in this direction, be kind of like the wind pushing on an airplane that's trying to fly in this direction. It maintains that direction. Our angle here is less than 90 degrees, so we're going to use force times the change in that position times the cosine of the angle. So sine is still positive because we're still speeding up. If your force is at a 90-degree angle, then you'll notice that it has no bearing on the direction of motion. Because of that, there's no energy transfer in the direction of motion, and the speed and the kinetic energy are kept at a constant. For the very bottom one, you'll notice now that the force is greater than 90 degrees from the direction of motion. Or from our displacement. So because of that, we're still using FR cosine of the angle, but because your angle is bigger than 90, you're going to get a negative value for your energy and kind of what's happening. So here, our sine of the work is negative. Sine of the work is also negative if you're at 180 degrees. And remember, the cosine of 180 is going to be -1. So energy here is transferred out of the system and the particle slows down. So that's just some ways to really look at what's going on. So if I have a force perpendicular to the direction of motion, that force, a force everywhere perpendicular to the direction of motion, doesn't do any work. So the friction force on a car turning a corner doesn't do any work. Neither does the tension force when the mass on the string is in a circular motion. Same thing if you are a waiter or a waitress and you are carrying around a plate of dishes. So if you have that plate of dishes, when you move in this direction, your force is at a 90-degree angle. So as you work during the day, if you're just carrying a load of dishes, you're doing no work on the dishes. Okay? I realize your body's doing work, but we're looking at just the dishes themselves. When you set the dishes down, or you pick them up, now there's work being done because now you're going in the direction of motion. But here, because you're holding it up and then you're moving in this direction, so here your force is in this direction and your delta R is in this direction, it's 90 degrees and that's 0, and that means that you're not doing any work. Same thing in terms of turning in a circle. So if you're turning at a constant velocity, notice that your force vector is centripetal force and it is pointing towards the center. It's really not centripetal force. That's not a true thing. Instead, it would be like the normal force or some force of friction pointing towards the center. But nonetheless, there is no work done as that is moving by definition. Let's go ahead and move down to the next page, which is the work done by a variable force. So when you have a variable force, notice that I no longer have just a constant force, but our force starts at one place and then it is increasing as we go through. We can still find the area, but we've got to use calculus now. So here we know that work is equal to the definite integral of Fs ds, where we're starting at some position and ending up at another position. So this is the area under this curve, and the integral really just sums up all the little tiny amounts of work that you're doing as that force is increasing or decreasing over time. So let's use the equation in order to find the work here done with a force versus a position graph for a car. So you have a 1,500 kilogram car. It does accelerate from rest, and this picture shows the net force on the car. So that's propulsion force minus any drag as it travels from 0 meters to 200 meters. So we want to know what is the car's speed after traveling 200 meters. Please be careful. This is not a position versus time graph. This is not a velocity time or an acceleration time. It is a force and it is a position graph. So we want to watch out for that. Since our original velocity is equal to 0 meters per second, our change in kinetic energy is just going to be equal to 1/2 mv final squared minus 0. And so this is the net work that is being done. We know that our original position is equal to 0, so there's our original position, and we're going to say that that net work is equal to the definite integral going from 0 to our final position. And we're going to take this and we're going to say this is the net force in the x times dx. Net force times x dx, sorry. This is really just the area, okay, under, and then we're going to say the net force in the x direction versus x. So that's this area right here. Because of that, we're just going to say that the net work is equal to 1/2 of the force, which is 5,000 newtons, times our 200 meters. And that is equal to 500,000 joules. So this is by definition the net force in the x dx is really just that area underneath. So once we know now how much work is being done, because this is the change, we find out that it's 500,000 joules, we can go back and use our equation here to figure out what the speed is. So if I have work is equal to 1/2 mv final squared, and I want v final, we will multiply both sides by 2. So this will be 2 times the work, net work, which is the change in the kinetic energy, all over the mass, and then because it's vf squared, we have to take the square root of both sides. So we're going to end up here with 2 times 500,000 joules, all divided by our mass, which is 1,500 kilograms, and we end up with 26 meters per second. So the calculus here is really just our equation. We know that it's just the area under the curve, so since this is a variable force, but it's not doing anything weird like this, then we can just find the area under the curve, and that makes it a little bit better. The next topic that we really badly need to go through is work and springs. So remember, whenever you have a spring that is stretched or compressed from equilibrium, it does negative work since the spring is pulling in the opposite direction of motion. So it doesn't matter whether I take the spring and I compress it in one direction or I stretch it in the other, I always will have the work done by the spring is going to be negative. So that's negative 1/2 kx squared. So the x here is kind of independent as to what's going on. If you compress it and you say that's negative or this is negative, then it ends up being positive because of this squared. So the negative comes through an understanding and not really through the math. So here the work done by the spring is negative. The work done on the spring is positive, so you have to be careful with that. The force doing the stretching does positive work, equal to the magnitude of the work done by the spring, which is negative. So here is the positive work that is done to stretch the spring, and this is the work the spring does, because it is always resisting. So springs always resist. They resist whether you stretch them or you compress them. And because of that, then we say that the work is always negative. If we think about the work energy theorem for a spring, we can go through and kind of look at this example. So this is called a pin cube machine. It's not a pinball machine, otherwise this would be a ball. It's a pin cube machine. It's an ill-fated predecessor of the pinball machine. That's a joke. You have a 100 kilogram cube. It's launched by pulling a spring back 20 centimeters. So notice that this stretch is negative 20. And the thing that we're doing here is we want to know what is the launch speed as it leaves the spring if the spring constant is 20 and the surface is frictionless. So this is allowed to continue to travel. So in this problem, we know our forces. We have the force of the spring pointing to the right. The normal force up and the force due to gravity down are equal and opposite, so they are also at a 90-degree angle, which means that we don't have to worry about those forces in relation to the motion that we have itself. So let's go ahead and go through and solve this one. We know that the change in energy here is only kinetic. So we've got a change in kinetic energy that's equal to 1/2 mv 1 squared, because we're going to be over here. We're looking for V1 minus 0, and that is the work that is done by the spring. We also know that the force of the spring times x, so the force of the spring times x is equal to negative k delta x. So that's by definition the force of a spring in the x direction is really just negative kx. So I think, let me rewrite this. This is the force of the spring, and we're thinking about x, and so that's equal to negative k delta x. And so here we're just going to say that's negative kx because we only have the one value that we worry about. The force of the spring is positive because x is always negative. So now what we're going to do is we're going to say the work done by the spring is equal to the integral of our original position to our final position. And we've got the force of the spring in relation to its direction, dx, and that's equal to negative k times, and so here we go, we've got x0 to x1, and the k stays on the outside because that is the force of the spring. That's a constant, so we're going to move it to the left. The negative is also a quote-unquote constant, and now we have x dx. Because I don't have any value for xo, well actually let's go ahead and put that in. So this is going to be equal to negative 1/2 of kx squared, and we're going from x0 to x1 is our boundaries there. So let's go ahead and do the integral here. So we're going to say this is equal to negative 1/2 kx1 squared minus 1/2 kx, and that's our original or our 0 position squared. The work, the WSP for this, for x0 is equal to negative 0.20 meters, and we're looking at it going to x1, which is 0 meters. So that's essentially what's happening. We've compressed it, so we've gone negative 0.2 meters, and then it extends out to where it's no longer extended, and that's where it has released all of its energy. So the work of the spring then is equal to 1/2 of the k value, which is 20, times our x, which is negative 0.2 meters squared, and then we don't have any value for this one because it is 0, and so that is equal to 0.4 joules. If I want to know what the speed is, we know that the speed at position 1 will be equal to the square root of 2 times the work done by the spring, all divided by the mass, and we did this earlier in terms of finding that equation. So that's equal to the square root of 2 times 0.4 joules, all divided by 0.1 kilograms, and so you'll end up with 2.8 meters per second. So this is the way the College Board goes through and helps you kind of see how springs work and kind of where their energy comes from. So that is the end of part 5.